Good afternoon, everyone. Today we're here to discuss the advanced concepts in artificial intelligence and machine learning. We have fantastic presentations. They're all highly distinguished speakers, so I think it'll be a very interesting session. I'm Duncan McCarthy. I'm your moderator today. So if you have any questions, please feel free to put them in the box at any time, and I'll be able to read them out to any of the speakers. Without going on too much more, I'd like to introduce Dr. Curt Davis. I've been friends with him for many years. He got his doctorate at the University of Kansas in 1992. He is the Naka Endowed Professor for Electrical Engineering and Computer Science at the University of Columbia, Missouri. And he and I worked together a long time ago to establish the Center for Geospatial-Intelligence at the University of Missouri. And for over 30 years, his research has involved the use of satellite remote sensing systems for numerous applications, including ice sheet monitoring, change detection, geospatial information processing, and national security. I worked with him a long time ago on two things called GeoIris and GeoCDX, which were really cutting edge for the day. His current research is focused on the development and application of deep machine learning methods for object detection and scene recognition in large volumes of high-resolution imagery. So without further ado, I will let Curt take over. You will not be seeing Curt today in person because he is actually broadcasting from the facility in which Curt and I installed down there at his university, and from there, the NGA mandates no cameras being allowed. So you get to see his slides, but not him.
All right. Thank you, Duncan.
Sure.
So great introduction. And I've been working kind of in this problem space ever since we started the Center for Geospatial-Intelligence. And today I'll be talking about a 2-year effort funded by NGA through their NURI program. And what we're focusing on in here is how we can take machine learning algorithms and assist humans in object search and detection problems, in this case over North Korea. And not just assist them, but we also want to quantify how they impact the performance of human visual searches. And so the opportunity that is really there, and you can look at this slide that was put out by NGA, which I've copied here, is if you can see the bottom half of this quad chart, more than 65% or about 65% of the time that NGA analysts spend, and this was as of 2019, is spent basically looking for known targets. And this presents a great opportunity because if they're known targets, that means we can label data, train machine learning algorithms using the labeled data, and hopefully assist them in their applications. And then the idea would be that we can move from the lower half of this quad chart to the upper half of the quad chart, where we're allowing the analysts we're freeing up time and labor spent on the lower part and freeing up their time in order to look for more complicated problems and unknown targets and patterns of life and things like that. So we've been doing this research for quite a while. So this leverages something we published back in 2017. And this was an example of a very great success, which is why we've actually continued the work. And we demonstrated it back in 2017, searching 90,000 square kilometers of an area in Southeast China looking for SAM sites. And we did this a traditional way, and we did it with a machine-assisted way. And we could search that area using machine-assisted searches 80 times faster than the traditional search that we did for the benchmark. And that was only done in less than an hour. And it turns out that the search accuracy using the F1 score as the metric was the same for both the traditional visual search as well as the machine-assisted search. That's a great result. Since then, we've continued to evolve our approaches, and this was a result from the GeoInt Symposium in 2019, where we further refined our algorithms. And now the top 5 results, and this is just people walking up to a booth and logging into a website demonstration that we have using some of the improved algorithms, they're actually able to search that entire 90,000 square kilometer area in less than 2 minutes with an F1 score of greater than 96%. So, and that's about 700 times faster than the original traditional baseline visual search. So fantastic result. So the question that really launched this effort is, well, can this be repeated for other objects, targets, things like that? And so that's what we're trying to do here. We're trying to take these machine learning algorithms and test them on a wider variety of relevant military and foundation GeoInt feature object classes. We got input from NGA analysis branch chiefs in order to select some of these. We want to apply them to the commercial high resolution EO data sets available through Digital Globe's web services, web streaming services. And then we're going to do traditional searches and then machine assisted searches, and then try to quantify the performance of both and do a comparison. And we chose North Korea because it was technically challenging. It was a modest country size, high relevance in terms of mission relevance and interest within the DoD and the IC. And it's also a very high degree of technical difficulty, much more so than our original study that we did for Chinese SAM sites because of terrain, seasonal and weather effects, tactical concealment. In fact, here's an example. These are some SAM sites from that original study that we published in 2017. This is some examples of what SAM sites look at in North Korea. Much more concealed within the vegetation and much more well hidden. And so much more difficult to visually even look at that and say that's a SAM site. It would take more training and expertise to do that. Here's an example of a satellite dish from some of our training data. That's in samples from different locations in the world. Here they are in North Korea, where they've camouflaged, painted the parabolic dish to try to conceal them, and also placed it in surrounding vegetation. So that's just an example of why North Korea is a much harder problem for the machine learning algorithms. And so in order to do this, we have leveraged a lot of work that we've done over the last 5 years in order to be able to tackle this particular project, where we want to do this for a wider variety of feature and object classes. And so just a little bit of background on that. 5-6 years ago, we started curating and labeling our own data in this for the high resolution commercial imagery. We've to date curated more than 3.5 million features and objects. About a third of those are kind of in the military classes, and I'm illustrating those here kind of in the bottom right. So these are TELs and mobile radars and mobile communication vehicles. So about a third of our labels are for military type classes, and the other 2/3 are from what I call foundation GeoInt classes. So things about infrastructure that are static and not mobile, and that you would kind of want in a mapping type of product. So we have that data set, and we've got a pipeline that takes our data, does very advanced training and testing and validation of the machine learning algorithms. We have high performance computing to be able to apply those algorithms at scale. And so all of this kind of existed before this effort. And what we had to do in this effort, we had to develop a UI UX that would allow us to then present the machine assisted detections to a human analyst, have them review it, but the UI UX is actually integrated with the database, so we can also gather timing metrics and do a bunch of things because it's tightly integrated with a custom database that we integrated into the system. So it's more than a UI UX. It has a back end that helps us mine the results of that. So I mentioned earlier that we had NGA analysts, branch chiefs give us input on what to select for the studies that we did of this. And they gave us a list. We had our own list. We kind of conflated the two and came up with a list of 20 that we were going to study in this particular effort. And 15 of those 20, or 75% of them, came from the NGA input, or the branch chiefs that provided input. So we thought, it's a pretty good mapping there between, kind of their interests and what our interests were from kind of a research perspective. This is examples of those one chip examples for each of those 20 feature and object classes. This has the first 10. I'll pause there. I'm not going to read all of these out. We see some communication towers, military vehicle groups, clusters of military vehicle groups, some foundation GeoInt type of things, like the cooling towers and communication towers, satellite dishes, helipads, things like that. Second set of 10. So now we're getting to some more military things, although there's still some foundation GeoInt. So power substation, obviously a foundation GeoInt type of class, but we have artillery positions, AAA sites, SAM sites, of course, because we've had 5-year history of studying those, UFAC portal, power pylons, things like that. So those are the 20 feature and object classes that were selected for the study in this effort. This shows an example of our existing training data that we have for those 20 feature and object classes that are here on the x-axis. And so this is showing our entire holdings within our data set across those, and then also the North Korea, and I'm just going to go ahead and flip to the North Korea focused version of that. So for North Korea samples, we have, obviously lots of power pylons, but 12 out of the 20 object classes or feature object classes that we selected had less than 500 North Korea samples, and 6 out of 20 or 30% had even less than 100. So some of these are fairly rare, at least within our data holdings, and they're actually fairly rare in general. Especially in terms of the data that we had available to us in North Korea. All right, so in terms of the imagery, we are using the Maxar Enhanced View web hosting streaming services. We downloaded all of North Korea, the image base map, which is a product that's produced by Maxar. And so that's illustrated here on the left-hand side. In addition to the base map, we then also downloaded the 3 most recent, at the time we downloaded them, what we call strip map collects, which are not processed into a base map. They're not raw, but they're not further processed into a base map. And so we downloaded up to 3 for those, although in some areas we only get 1 or 2, and you can kind of illustrate that, see that illustrated in the chart. So in project year 1, we used the ortho image base map for both the traditional visual search and the machine assisted searches. And then in project year 2, we repeated what we did in project year 1, but only for the machine assisted searches using the strip map imagery for the inference. Now, again, the visual searches were done only on the base map because they're cloud free, high guarantee of coverage. And so that's why we use them for the visual searches. But machine assisted searches were done in both years, but again, with different imagery sources for the inference. So this is an illustration of, and we download all this imagery. We created our own WMS service internally to host the downloaded imagery that would integrate with our web UI UX. So this is an illustration of our WMS service that we created for the base map. And the traditional visual searches were done within Esri ArcGIS plugin that accessed that WMS service that we created internally. So we would have a grid, and then the search analysts would do the visual searches using that ortho image base map, and basically this ArcGIS Esri plugin to actually annotate when they found the objects or features of interest. And we use the ortho image base map for the visual searches because excellent coverage, very low cloud cover. So it's very well suited for the traditional visual searches. So in terms of what we did for the visual searches, for each feature object class, we searched 2 quarter geocells, so quarter degree by quarter degree in latitude and longitude. Those are roughly 600 square kilometers each per quarter geocell. We had 3 or sometimes 4 student analysts that were doing the visual searches. And these were all students that had previous experience interpreting satellite imagery. So these had all worked on different NGA Foundation GeoInt contracts. So they weren't just like raw, students with no prior background in this. The average amount of hours, labor hours they'd spent doing Foundation GeoInt type feature extraction on NGA contracts was 700 hours. So this is a good, set of students that we could use for doing this because they had prior expertise in analyzing at least Foundation GeoInt. Now they didn't have the expertise in analyzing the military type targets, but that's still a very good starting point in terms of student labor and experience for undergraduate students. This was the lab that we did those searches in. It was dedicated for both the machine and the traditional visual searches. And we started this effort right during the height of COVID in 2020. And so even though the campus was shut down, a lot of these students volunteered and came in and were doing some of these visual and machine assisted searches in the spring and summer of 2020 when the entire rest of the campus was shut down. So very dedicated group. And they did it obviously as volunteer, it wasn't mandatory. So summary here of how long it took them on average. So we measure how fast they do these visual searches, and we've got this plotted here by the different feature and object classes. So on average, they could search these corridor geocells at roughly 125 square kilometers an hour, the fastest being the military vehicle group, and the slowest being the power pylons in terms of that. But the average was about 125 hours. If you're extrapolating that to like how long would it take to search all of North Korea for one of these things, on average, that would be about 1,000 hours, or basically half a person year, in order to execute such a search over a country-sized scale. So we've got the search times. We can also then actually score how well they did in finding the features and objects of interest against our ground truth. And so we actually calculate the F1 score. I think this is a machine learning session, so I'm not going to talk about what the F1 score is, but that is the overall metric that we use to assess it, because assess these performances, both traditional searches and visual searches, because it considers both false positives and misdetections or false negatives. And so it's a good overall metric to do that comparison. So on average, the traditional visual searches had an average F1 score of 52%, which goes to illustrate how hard it is just doing regular searches, right? To find objects, especially in North Korea, because there's going to be a lot of things that are missed. There can be some false positives because of image interpretation error, but on average was 50% for these. Storage tanks were the easiest. SAM sites, and I showed you some examples of SAM sites earlier about the challenges in North Korea. They were the hardest. All the way from, going from 92% F1 on the storage tanks, which are large and usually not well concealed, all the way down to SAM sites at 13%. So to summarize these results, we searched 71,000 square kilometers of land area, 133 different corridor geocell searches, because we're doing multiple searches per corridor geocell with multiple analysts. Half of the objects and feature classes had a recall less than 50%. So even the traditional visual searches are quite challenging. And the per class average, again, on the F1 was 52% for those traditional visual searches. So then that leads us to the machine assisted part of this. There's a lot of technical details that I just cannot go into here, but we looked at a wide variety of different architectures that we're using, training strategies for both the true negatives and the true positives that go into training the machine learning algorithms. We had validation data, of course, it was withheld from the training data sets in order to independently test the candidate machine learning algorithms. And the bottom line out of all this is we only went forward with the machine assisted searches for 14 out of the 20 feature object classes, because for 6 of them, we just felt we couldn't get a good enough validation score to even warrant doing that. So this shows just the train test metric. So it's an 80% train, 20% test type of thing in terms of a train test split. So we're looking at the precision recall and the F1, but this is ordered by the F1 score. So again, we can get some very good performing models here, F1 scores, above 75, 80% for most of these, but then you start to see it drop off down to the 20% range for some of these military targets like here, helipads and military vehicle groups. And then these were the 6 classes over here on the far right that we could not get a DNN that would generalize well enough on our validation data for us to go ahead and proceed with this. So that's just the models. That's not the machine assisted searches. And so we have this custom UI UX that we developed to be able to score these. So we have the machine assisted detections that are presented in this user interface. The analysts can accept or reject. There's a further review button here that was not used for this study because we wanted them to make a binary, crisp decision on that. And so they're able to review the results both zoomed in and in context. For other uses, although weren't used in the study, we had the ability for them to add tags and annotations and things like that for other types of studies that we could do. And so this is a summary of the average search rates for both year 1 and year 2 for the machine assisted searches. So the average search rates here for machine assisted searches in year 1 was about 1,400 square kilometers per hour, which is about 10 times faster than the visual searches, and 3,700 square kilometers per hour for year 2. So significant improvement in the search speeds and time, reduction in the search speeds, or the search times in year 2. And that was about 30 times faster than the traditional visual searches. And you can see the scoring here by, what was the fastest. The cooling tower fan groups were the fastest. Artillery positions, tank groups, those were some of the slowest machine-assisted search times, primarily because they had lots of false positives, right? So your machine-assisted search times are going to be largely driven by how many false positives you have to review. So that's what's going to create the slowdown. This is looking at the recall or the true positive rate of the year 1 and year 2 DNN. So we did make improvements between year 1 and year 2 on average, although some in year 2 were not quite as good. But the average improvement in the recall for the machine learning algorithms is about 12%, compare year 2 versus year 1 for the 14 feature and object classes that we studied. And you can see just an illustrative example of that here. So this is looking at AAA sites specifically. So in year 1, we had, compared to year 2, we had a 11% gain in the recall or the true positive rate, and we had a almost 2.5 times reduction in the amount of false positives per unit area in year 1 versus year 2. And so that's where you're seeing right here. This is where you're seeing the kind of like the 2.5 or 3 times improvement in the overall search speeds or search times for the year 2 searches. So this is now looking at the year 1 versus year 2 machine-assisted search F1 scores. So not comparing yet with the traditional visual searches. And so 9 out of the 14 feature and object classes had a better machine-assisted search F1 score in year 2 than they did year 1, an average improvement of about 5% over all those classes. And this is kind of the money chart right here. This is looking at everything in terms of the F1. So we have the traditional visual searches. We have the year F1 scores. We have the year 1 machine-assisted searches F1 scores, and the year 2 machine-assisted searches F1 scores. And so overall, comparing just the F1, using that as kind of our primary metric, in year 2, we were able to get 5 out of the 14 feature and object classes, or about a third, had a better machine-assisted search F1 score compared to the traditional visual search F1 score. And you can see the average here across all the classes for both the year 1 machine-assisted and year 2 machine-assisted. So it went from about 45% to about 50%, whereas the average F1 for the visual searches for these 14 feature and object classes was 55%. So the machine-assisted searches are not far off in terms of average F1, but they're still on average not quite as good as the traditional visual searches. So to kind of wrap this up, we've developed a really end-to-end framework: training data, train test validation of the machine learning algorithms, applying them to large volumes of high resolution imagery at scale, and then being able to really get to the end user, so to speak, at least internally, where we can use these detections from the machine learning algorithms in a UI UX designed to measure human performance. And so we did that. We did the visual searches for 20 feature and object classes covering about 71,000 square kilometers. We did the machine-assisted searches for 14 out of those 20. We could not get the models to generalize well enough for 6 of those classes. And then we compiled key metrics to quantify the human performance of the visual searches, the traditional searches, versus the machine-assisted searches. And the machine-assisted searches were obviously much faster compared to the traditional visual search. So that's a big benefit in terms of speed, 10 times faster in year 1 and almost 30 times faster in year 2. But we still have a long way to go. There's still more work to done to improve these algorithms. The average F1 scores for the traditional searches was only 55%. And the average F1 score for the year 2 machine-assisted searches was 50%. So very close, but still not equaling human performance in terms of that. In the areas where the traditional visual searches were better, on average, they were better by 21%, but in areas where the machine-assisted searches were better, they were on average better than by about 22%. So there's still a lot of variability in the performance of these algorithms based upon the type of feature and object classes we're going. And to kind of really summarize all this up, I think the machine-assisted search algorithms did very well on what I would call larger distributed object or feature classes. So you got sites, positions, a group of cooling towers, a group of helipads, a SAM site, and they did not do as well on your smaller and harder to generally smaller and harder to distinguish feature and object classes. And that kind of goes with our intuition, I think. So with that, I do believe we do have a few minutes left for questions. And so I'm going to turn it back over to Duncan McCarthy, who I still want to come to get his PhD here at MU. You know, it'd be great if you could carve out a few years. We'll work together some more on the tail end of things. Oops, I cannot hear Duncan.
I would love that. All right. A couple. One question popped in. So the question is, have you considered applying these ideas to lower spatial resolution planet scope imagery? The person says on a past project they worked with researchers on a nonprofit focused on non-proliferation. Their staff would spend a significant amount of time each day scanning the most recent planet imagery of North Korea. For changes. So they might be able to benefit from that work.
Right. And so definitely have considered it, but I have no basically funding sources to be able to pursue that. You know, obviously, if we go to planet resolution imagery, we're not going to be pursuing some of these higher resolution features and object classes. But things like SAM sites, AAA sites, you know, those things could be observable, you know, fairly reliably in planet imagery. And so everything that we've done here is actually agnostic to image source. I mean, literally, except the fact that we've labeled and trained a bunch of high resolution imagery. So that's not agnostic. But the rest of the pipeline that we developed could be applied to SAR. It could be applied to lower resolution EO. There's really nothing other than, again, our training data that is source specific. So the methodology and the framework that we've developed here could be applied certainly to planet and other imagery sources, black sky, commercial SAR, et cetera.
Oh, that's great. Yeah, it'd be very interesting to do this with SAR as well. It's a neat study. See, another question. How long does it take to sort of train up to recognize a new feature, and kind of what's the minimum data set size that you would recommend for doing that?
Well, more data is always better. Okay, now some of these things we have thousands and thousands of samples, and more data is really not going to help, right? Yeah. And you know, example, Power Pylon was one of the feature object classes that we had 30,000 samples on, and we didn't even with that level of samples, we couldn't get a good performing machine learning algorithm to train against it, right? Because it was just so hard in North Korea. So more data there is probably not going to help. You have to spend more time on better algorithms and more advanced approaches than what we're able to do here. So more data is always better. I really can't recommend a minimum because it's highly variable based upon the size of the object. It's not just the size, but it's also its distinctiveness relative to feature and object classes, right? So if it's something very distinct, you're going to need fewer samples. And then you've got the biome, right? If you're flying these out in the Middle East in a desert, these things are going to stand out and light up like Christmas trees compared to North Korea. So you've got a whole bunch of factors that are going to really affect, you know, what kind of, you know, your intuitive minimum sample size is. Now, having said that, we have demonstrated for, you know, that earlier SAM site study, we've demonstrated you can use less than 100 samples and still get good results, but it has to be under the right conditions.
To sum up, it depends and it's complicated, right?
Yeah.
All right. Well, thank you very much, Curt. I think we are now out of time. And so thank you everyone for attending. And we'll talk to you in 8.5 minutes.
Right. And if there's follow-up questions, I do have to go teach a class, so I may have to leave here. But if there's follow-up questions, you can get in touch with Duncan, or he can give you my email or whatever, and I'm happy to follow up either virtually or even on a phone call. So Absolutely. With that, thank you very much.
Thank you, Curt.